KP hierarchy. So I want to tell you, in my mind, one of the most beautiful theory in mathematical physics, which you can see how one topic, one object called KP hierarchy relates analytic, analysis, and geometry, and also a certain kind of algebra called vertex algebras in mathematics. So we are starting from a partial differential equations. So differential equations are one of the most interesting and important objects to study because it appears literally everywhere. So in math, in physics, in biology, in chemistry, in social science. So you can say that the differential equations govern our universe in a certain sense. So at some time, actually it's around the 1970s, so two Soviet physicists called Kadomtsev and Petviashivili. So their initials are given by K and P. So they write down this equation to describe a propagation of the shallow water around a plane. So you can view this U as the amplitude of a water or water wave propagating along the plane with time t. So it's governed by this equation. So some of you may know that the right hand side here, this equation, if we set this to be 0, you get the KdV equation, which is an important equation in mathematical physics. But anyway, so they soon find that this is a very, very nice equation, meaning that you can solve it exactly for some certain solutions, and these solutions behave very well asymptotically. And actually, they find that this single equation is actually a number of an infinite number of equations. So in mathematics, we call this infinite number of equations a hierarchy. So they are actually in a family. So it's given in this way. So we consider this operator here. So I will not explain what's the meaning, but you just know that this is kind of operator, and you can take its power and take a certain sense in a positive part and taking the commutator here, and you get an equation. So it's I will not go into detail, but you need to know that this system if equation consists of infinitely many unknown functions here. So all these u1, u2, u3 are unknown functions in our system. So here u is actually uy here. Uy here. So literally this is actually the second equation of this system. And it has infinitely many equations. So here k can take to be any integers from 1, 2, 3, 4, 5, something. So we have a huge system, infinitely many functions and infinitely many equations. So naturally, this is very hard to study because mathematicians are not, unlike physicists, are not good at dealing with infinite. So the first question is, okay, how can we reduce this system into a simpler form? So in 1980s, so there's a group of mathematicians in Kyoto University, now they are called Kyoto School. They deeply studied this kind of system, and their leader, the great Japanese mathematician Mikio Sato, find that, okay, we can reduce this huge system into a system of single function. So this is a huge reduction from infinitely many to only one. So this single function is called the tau function. And he found that this huge system is actually equivalent to the system here, the equation here, for this tau function. Okay, so you may see that, okay, actually this is only one equation, and for one unknown function, everything's fine. But actually it is not. It is still infinitely many equations because we need this identity to hold for any t1, t1 prime, t2, t2 prime. So actually we have infinitely many constraints. But something nice is that at least we reduce the number of unknown functions. And once given this tau, we can solve this u1, u2 in this sense. And conversely, if you solve u1, u2, you can find some tau satisfying this equation. So this is literally equivalence. So from a physical point of view, we can view this tau as a certain partition function of certain quantum field theory, and each UI is a multi-pointed correlation functions here. So this is a physical viewpoint. So naturally, we want to find some example of this solution. Actually, although this system is quite complicated, but we can find some very, very simple solutions here. For example, the constants, 1 is a solution. So these simple polynomials in T1, T2, T3 are some simplest solutions that has been ever discovered. So these are called Schur polynomials. They are labeled by partitions. So a partition is a diagram. So like here, so it's a diagram of blocks. So for example, this one corresponding to open the empty diagram. This corresponding to these two blocks put in this way, and this corresponding to two blocks put in this way, and this corresponding to 3 blocks. Also this one. Also this one. So I think many of you is quite familiar with this kind of diagram. So these are historically these are somehow first solutions that is discovered. So a question is what's the general solution? So for example, let us consider up to degree 4. So we want to consider all the solutions that can be written in a somehow linear combination of Schur polynomials with at most four blocks. So okay, naturally you have this indeterminate C lambda as unknown coefficients, and we feed this tau back into this equation, and we solve C lambda. So this is quite actually quite simple, especially when you're using computer software to solve this. And you can still find this kind of relation. So this C lambda cannot be arbitrary. So at least they need to satisfy this very nice and very beautiful relation. So Sato soon discovered that this is nothing but the pre-correlation for Grassmannian. So now we will change to the geometric side. So we are interested in an object called Grassmannian Mn. So this is m-dimensional subspace in n-dimensional space, linear subspace. So for example, on this is a one-dimensional space in two-dimensional case. So a two-dimensional case is a plane over this real number. So all one-dimensional linear space are simply lines crossing this origin. So you can see all the lines are given uniquely by this angle. So this space is the same as angle 0 to pi. But of course, 0 and pi will give you the same line, the x-axis. So you need to glue this endpoint of this interval, and you get this circle. So over real number, this space is nothing but a circle. And you can also argue that over complex number, this space is a sphere. So generally, the key fact here is that generally the Grassmannian is a algebraic variety. So in Chicago's talk, he has already told us about algebraic variety. So they are spaces defined by solving polynomials. These polynomials are called pre-correlations. So for example, in this GR24 is given by the solution of this equation. So you see that this equation is the same as this equation. But the only thing is that we have infinitely many t variables here. So Sato argued that actually the KP tau function is the same as this is somehow weird formulation, but it is the half infinite dimensional subspace in infinite dimensional subspace. So this has a explicit mathematical meaning, but we are not going here. So we already relate the solution to this geometric space. This is very nice in the sense that we can write down all the polynomials that define it. Now we go to a even more striking thing. We can describe it in a completely algebraic way. So let us introduce a Fermion algebra. So I think now we are in some stage that many of you may be familiar. So we introduce psi and psi star here. We can think of it as creation operator and annihilation operator of electron and positrons. So you can view this as electron, this as positron, with n positive giving the annihilation operator and n minus giving creating operator. And they satisfy this canonical cumulation relation. So they are Fermion, so this commutation is actually the plus sign, as you know, not the minus sign. So this creation and operation, annihilation operator acting on the Hilbert space of in the QED. So we use the idea of Dirac. So this operator acting on Dirac C. So meaning that okay, we have a vacuum, and this creation and annihilation will excite the states, give you excited states. So mathematically, this Dirac C form a representation of Fermion algebra. So using this Fermion algebra, Sato find that all the KP tau function can be written in a very beautiful form. It's like physically, it's like evolving a state, right? And consider its vacuum expectation value. So here, H is a Hamiltonian. So the explicit formula is here, but it's not quite important. And here is the initial state, and it evolves with this Hamiltonian. Here, G is a quadratic Fermion of this form. So since every tau function is of this form, we see that the space of KP tau function is the same as vacuum orbit, right? So this is called a vacuum orbit. So actually all the G is actually invertible. So every two excited states of this form can be related to each other. So it's called an orbit. And a state in such an orbit satisfies this equation. So finally, we are in a state that we can rewrite the KP system, which consists of infinitely many functions and infinitely many equations, into a single equation, literally single equation of a single unknown function W here. This is a state in the Dirac C. And another interesting thing is that the right-hand side, left-hand side here, tau function is a bosonic object, meaning that these t variables are simply commute with each other. But the right-hand side is a Fermion object, meaning they anti-commute. So this relation is called boson-Fermion correspondence, which is a important idea in physics and introduced by Sato school to mathematics to formulate their KP theory. So a one word take away information is that through this algebraic and geometric and analytic language, a huge system can be reduced into a very single form. So this is the meaning of integrable. So this is why integrable systems are interesting. Okay, so I'll stop here. Thank you very much.
Okay, so let's take the question from non-expert and younger people. Any questions from youngest or non-experts? Yeah, you qualify.
Thanks for the interesting talk. So my naive understanding of Yang tableau is to formulate some sort of symmetry.
Yes.
But what is the associated or corresponding symmetry, the original equation?
The symmetry actually is here. So the group of quadratic fermions. So this group is GL infinity. So you can imagine this as a infinity matrix which is invertible. So this is the symmetry.
Okay. But this symmetry is not explicit in the KP equation.
Yes, not explicit. So this is why this language is essential here. But purely from this, you cannot easily see this.
Well, right.
Yes. there is a way to see this, but it is somehow artificial. I think a correct logical way is that first you discover this, and then you find, okay, this is the hidden symmetry of KP. Yes. This is also the historical example. Yes.
Let's ask more any other questions because you have some work done related. So maybe more layman's questions, naive questions. Okay. Actually, it is a question with some mathematical knowledge, so maybe more kind of stupid questions. Okay.
Thank you. So, I'm a bit confused about the left side of blackboard. So tau is a function with infinite variables. But
Yeah.
Your u is a function with three variables.
U is also a function in infinite many variables.
Then
Yeah.
how do you? So what the relation between u and ui is?
U and UI.
Yeah.
Here, you mean this U?
Yeah.
This U is U1.
I
Yeah, this U is U1, and U and tau is related by this
Ah.
function. And these are PDEs in U. So if you are strong enough, you can solve this PDE in principle as you solve all these UI as function of TI.
But u is a function with three variables.
No. I mean here, historically they only derive this, and they soon find that we can add in the dependence of U. Yeah, you can imagine this is the time dimension is infinite.
Yes. Thank you. Yeah, this is that.
Okay, that's good. Any more questions from non-expert? Okay, now let's ask Inari-sensei for.
From no expert.
But you know some of the parts.
So my question is very elementary. I suppose KP equation is a solvable equation.
So yes,
With a one well-known solvable equation, KDE.
Yes.
That KDE is in two dimensions, x and t.
yes,
And KP equation you write is x, y, t, so three dimensions.
yes.
And how somebody or Sato-san came arrived at this special form of equation with coefficient 4, 6.
This one.
Mhm.
So you mean this special coefficient here, right? So actually, in integral system, these coefficients do not is not quite important because we can somehow scale the time variable here. Since the important thing here is that this is nonlinear. So if you, for example, if you scale u, then this will scale one time, this will scale two times, and this will scale one time. So there is a one-time scaling here. So actually, you can scale the u variable, x variable, t variable to adjust these coefficients into any non-zero y you like.
So number 4 and 6 are sort of not very unique, but can be absorbed by gauge transfer.
Yes, of course, yes. The reason why we choose 4 and 6 here is because we want to pick this clean form u1, u2, u3 here. If you add some coefficients here, then you can adjust this one. Yes, this is all kind of.
Any more questions from experts?
Yes, the group. You can view it as a formal Lie group of a infinite dimensional Lie algebra of GL infinity. So you can imagine this. Yeah, you can imagine this as exponential. Yes. And this is strictly defined.
Why is a quadratic generates the G?
Why?
The quadratic polynomial generates G.
Basically, the reason is that you can naively thinking GL infinity has infinite many entries, and these entries are given by this one. Yeah, and if you compute infinitesimally, then the Lie bracket of this one is exactly the same as GL infinite.
Is it possible to see the integrability of this KP equation from the perspective of geometry?
Actually, yes, but it's not quite obvious. So you can think of the existence of this political relation is the same as integrability. Yes. Yes, because this relation is the same as the equation satisfied by tau, which is the same as KP hierarchy. Yeah. So the existence of this nice geometric structure itself is integrability.
Oh, thank you very much.
Let me kind of ask a question,
Yeah.
but maybe the same questions. But so from the geometric perspective, can you find any other integrable structure from just simply looking at the geometry?
Yes, of course. Because this KP hierarchy is somehow the universal one. So instead of this large space, we can somehow looking for the subspace of this large space. And they give you other integrable systems, like KDV system. KDV system also form a sub-Grassmannian of this person. Yes. And actually many integral systems also satisfy this kind of property.
Can I ask another question? So suppose you get one solution for that red box, W,
Yes.
and how do you recover tau from that solution?
Tau is this is W here. This is W.
Uh-huh.
So you only propagating using this Hamiltonian and compute its vacuum expectation value.
I see.
And this is a function in T.
T.
In
T has infinitely many.
Infinitely many T, because this Hamiltonian consists of infinitely many time variables.
Okay.
Yeah, but when you compute the expectation value, you can just view this T as constant. So after computation, you obtain some constant depending on T, which is a function T. So this is the tau function.
You mean T is T1 to
T1, T2, T3.
yes, yeah. And how is that? Is it like solvable in principle, or can you actually do hand?
Yeah, actually we can do it in hand. We can do it in hand. Yes.
Can you like use computers to generate all?
Yes, of
Oh, I
course.
see.
We can also do that.
Oh.
So everything is explicitly computable. Actually, according to some folklore history, everything is discovered by Sato by hand. Sato computed everything by hand, and he just found these structures. Yes.
Any other questions?
Could you give me the intuition of the form of the Hamiltonian?
Yes.
Okay.
The important structure here is that Hamiltonian. These Hamiltonian operators form a Heisenberg algebra. So this is the important here. So you may actually immediately understand. Okay, Hn is nothing but Tn, M is nothing but M partial of Tn, and maybe there is some minus sign here. So this is the these are the creation and operation operator in bosonic sign. So this is the idea of how we relate boson as Fermion. Yes.
Okay. Okay. Sure. Go ahead. So
Okay. So I think A is a fermionic VOA.
Yes. BC system.
Then so do you have a similar phenomena for other VOAs?
So this is a nice question, but actually, we have this boson fermion corresponds only for lattice vertex algebra, but no others.
Thanks.
Yes.
Thank you.
Well, my question is very naive. This fermion is defined in the 2+1 dimension or what kind of dimension?
Dimension.
Here, for example, in the say 3+1 dimension, you have to specify momentum, right?
Uh-huh.
And energy also. But
Ah.
you have only single n or
You can think this as 1+1 dimension.
1+1.
1+1. Yes, 1+1.
Okay. If everybody is good, then let's thank Zhe Wang, thank again. Okay, thank you very much for your.